Hello all, I am R. Tarun, Junior Core Committee member of IEEE Computer Society at VIT Vellore. Today I am going to give an introduction to computer vision. So what we are going to learn in this session? First, what is computer vision? Basic image processing, feature extraction, image classification, object detection, image segmentation, what is OpenCV toolkit, basics of OpenCV toolkit, and finally challenges and future potentials in computer vision. So what is computer vision? Imagine if your computer or smartphone has eyes like a superpowered detective. It could look at a photo or video and instantly recognize faces, objects, and even understand what's happening in the scene. The technology behind this is what we call computer vision. Computer vision is like giving machines the ability to see and understand the world through the eyes of cameras. These eyes are combination of advanced algorithms and powerful computing. So instead of just viewing pixels, computer vision enables to see the patterns, shapes, and information within images and videos, enabling them to identify a cat in a photo, assist self-driving cars in recognizing traffic signs, help doctors spot diseases in medical images, or even make your social media photos look cooler with filters are some applications of computer vision algorithms. So you can see in the top left image that this can be an example of finding the vehicle which uh, overspeeds in a highway. And the second image is an uh, example for self-driving cars, which helps detect the blocking objects or other vehicles in front of the car using computer vision algorithm. It is also used in medical industry to spot some diseases and other results. And for example, Snapchat, we all use filters. This is an example of computer vision algorithm to detect faces and other features. So the decision review system in cricket is also an example of computer vision and intelligent manufacturing and 3D reconstructions of objects like buildings and face detection in selfie camera are also application of computer vision. So now we will learn something about basic image processing. In computer vision, the raw material is the digital images. We are going to work with images. The digital images are made up of tiny dots called pixels. Each pixel represents a tiny portion or an image and contains information about the color. An image is essentially a grid of this pixel. So you can see in this image that it consists of different values. These values are called the pixels. Images have different channels such as red, green, and blue channel. For example, color images usually have three channels, which is red, green, and blue. And monoscale images, like black and white images, have only one channel, also called the grayscale. Understanding the image format is crucial in computer vision because it affects how we process and analyze the image. Image pre-processing is very important to apply many algorithms to the image for further application. In computer vision, we perform some various image operations such as resizing, cropping, and filtering. Resizing an image can change its dimensions, while cropping involves selecting a specific region of interest. Filtering, on the other hand, helps us enhance or suppress certain features within an image. If you want to concentrate on a particular part of an image, for example, in that highway road, if you want to uh, concentrate only on uh, cars, filtering algorithms can be used for image preprocessing. Cropping involves selecting a specific region or portion of an image while discarding the rest. Cropping also can help focus on the most relevant part of the image. These basic image operations are building blocks for more advanced techniques, and they play a significant role in image preprocessing and feature extraction. So we can see in this image that this is an example of a resizing. We are reducing the image size by 2 and again expanding it to the original form. Here we are seeing this image has a lot of noise. So we use some filtering to improve the image quality. And here for cropping to find the region of interest. Here, if you want to find the person vehicle number which is over speeding, where we need the vehicle number. So that is the region of interest. So we are cropping that part and focusing on. Now we will see some feature extraction. Now that we have a good grasp of image basics, let's learn about feature extraction. Features are distinctive patterns or characteristics within an image that help us identify and understand its content. There are various type of features we can extract. For example, edge detection helps us find boundaries within the image. Corners are points where the intensity changes significantly, and the blobs are the region of interest with a particular shape or size. These features are building blocks of object recognition. Think of edge detection as finding the outlines of objects. Corners are key landmarks and blobs as unique regions. By identifying and understanding these features, CV algorithms can recognize objects and patterns within images. Feature extraction is the first step towards making sense of an image, and it's an essential process in computer vision enabling image classification and object recognition. So the first image is an example of edge detection, and this is blob, and this is the other example. This is the corner detection, and this is the example of blob. Image classification. Image classification involves an assigning a label or category to an image based on its content. To accomplish this, we employ some ML algorithms. The most common ones are support vector machines and deep learning networks. These algorithms learns to distinguish between different categories by analyzing the features we extracted earlier. The process typically involves image preprocessing, which prepares the image for analysis, feature extraction, where we identify meaningful patterns, and then classification, where we make predictions. For example, we can train a deep neural network on a data set of images to distinguish between cats and dogs. Once we train the model, we can classify news images accurately. So this is a typical example of image classification. So it has various applications from identifying handwritten digits in OCR to categorizing image for content recommendation on social media platforms. Object detection. Object detection is a computer vision task that involves identifying and locating objects within an image or a frame. Unlike image classification, which only categorizes the image and it assigns a single label to the entire image. Object detection provides a bounding box around each object in the image and assigns a label to each of those bounding boxes. In other words, it answers the question, what are objects in the image and where are they located? Traditional computer vision techniques for object detection. The methods are used These methods use handcrafted features and techniques like Haar cascades, histograms of oriented gradients, and cascade classifiers to detect objects. Deep learning. particularly using convolutional neural networks, has revolutionized object detection. Several deep learning architectures, such as region-based convolutional neural network, it proposes a region of interest in the image and then classifies the object within that region. You only look once is another real-time object detection approach that divides an image into a grid and predicts the bounding boxes and class probabilities for each grid cell. Now we will see some applications of object detection. Autonomous vehicles. Object detection is critical for self-driving cars to identify pedestrians, other vehicles, traffic signs, and obstacles on the road. Surveillance and security. In surveillance system, object detection can be used to identify the intruders, track people, and detect suspicious activities. Medical imaging. In medical imaging, object detection can be used to locate and analyze specific structures within images such as tumors in radiology or cells in microscopy. Retail. In retail, object detection can be helpful with inventory management, theft prevention, and customer traffic tracking. Agriculture. Object detection is used for crop monitoring, disease identification, and yield prediction. Environmental monitoring. Object detection can be applied to track and count wildlife and conservation efforts. Now we will see something related to image segmentation. Image segmentation is a computer vision technique that divides an image into meaningful and distinct regions or segments. These segments are typically homogeneous in terms of visual properties such as color, intensity, texture, or boundaries. The goal of the image segmentation is to simplify and change the representation of image into something that is more meaningful and easier to analyze. Some image segmentation techniques. Thresholding. This is the most simplest segmentation technique. It involves selecting a certain threshold value, and all pixels with values above or below these thresholds are assigned to one of the two segments. It's commonly used for separating objects from the background in binary images. So here it's a simple example of thresholding. We will see more in the coming slides about thresholding. Region-based segmentation. Region-based methods group adjacent pixels with similar characteristics into segments. The most common algorithm is the region growing approach, which starts with the initial seed point and grows a region by adding neighboring pixels with similar properties. So if you want to uh, segment a person into different body parts to analyze the body movements, or also in fashion technology, if you want to check whether different clothes in a same person, this kind of segmentation will be very helpful. Edge-based segmentation. Edge-based segmentation focuses on identifying edges and boundaries in an image. Edges often represent object boundaries, and techniques like canny edge detector are used for this purpose. Watershed segmentation. Watershed segmentation treats the image as a topographic map and separates the region based on the idea that watershed lines should separate different regions, much like peaks in the landscape. Contour-based segmentation. Contour-based methods aim to identify and follow the contours of objects in an image. Active contours are an example of a technique used to detect object boundaries. So these are the different examples of different types of segmentation. This is the canny edge, this is the contour, and this is the watershed. Now we will learn something about OpenCV. OpenCV stands for Open Source Computer Vision Library. As the name suggests, it's an open source computer vision and machine learning software library. The library has more than 2,500 optimized algorithms, which consists of both classic and state-of-the-art computer vision, and machine learning algorithms. These algorithms can be used to detect and recognize faces, identify objects, classify human actions in videos, track camera movements, extract 3D models of objects, produce 3D point clouds from stereo cameras, and many other applications. To install OpenCV, I am using Anaconda prompt. In Anaconda prompt, I- if you type pip3 install opencv-python, the OpenCV toolkit will get installed. The first operation in OpenCV which I am going to teach you is accessing the image information. For that, first we need to import NumPy package, then CV2. So first I am importing NumPy as NP and importing CV2 as import CV2. To read an image, we use a function called imread, which is a short form for image reading. So I am assigning a variable img equal to cv2.imread, and we need to type the name of the image along with its image type. So opencv logo.png, and this is an optional parameter. Here one means we are reading the image as a color image. As soon as we read an image, we will get an output like this. This is the pixel values. Every image has pixel values. So it prints the values in the form of array. So if we type of image, we will get numpy.end array, which implies that image values are stored in the form of an array. And image.shape, img.shape, it gives the number of rows, columns, and channels in an image. So color image has three channels, namely red, blue, and green. So since we uploaded an color image, we are getting three channels. Now we will dive more into color channels. After importing the necessary modules, I am reading an image of an butterfly. And imshow function, this imshow function, it is used to display the image on a screen. Here we are giving the variable name of the image, and here this is the caption name. And move window function is to assign the position where we need to display the image in the screen. Here 0, comma 0 indicates that we are displaying this in the top left corner of the screen. Now using the shape function, I am assigning the three variables height, width, channels as height as number of rows, width as number of columns, and channels as number of channels, which is 3 here. And using the cv2.split function, I am separating the color images into its three color channels, namely blue, green, and red, and it stores the in the separate variables. Here, what I am creating is a new blank image. It's a NumPy array with three times the width of the original image. That's why I have given width into 3, because I want to display 3 images of the same butterfly. So I am using width multiplied by 3. So this code copies the channel BGR into corresponding segments of RGB underscore split. So the first part in that image, I am showing the blue values of the butterfly. Next is the green, and the third one is the red. And I am uh, captioning that as channels. Now you can see that after splitting the original image, which has three color channel into each blue channel, green channel, and red channel, you can see that On combining all these three values, we are getting this. So here, if you see that where and all the green parts is there, here it's a bit white color, and red part here it's bit red. So we are getting white around red. Now to convert this image into a HSV format, which is hue, saturation, and value color space. Now I am splitting them as HSV separate uh, values separately, and you can get the output like this. Now we will learn some pixel manipulations and filtering. So this line gray equal to CV2 dot CVT color RGB to gray. This line converts the color image from BGR color to grayscale using CV2.CVT color function. This results in a single channel grayscale image stored in a gray variable. Now I am writing gray.jpg, gray. These lines extract the blue channel, green channel, and red channel from the color image. Each channel is a single channel image representing the intensity of the color. Now using the merge function, the code converts CV2, the code uses CV2 dot merge to create a new image RGBA. It combines the blue channel, green channel, red channel to form the RGB components. And again, it also uses the green channel for the alpha. It's also called the alpha channel, which is a new channel in addition to the three color channels, which it is used to alter the transparency level. This means that the transparency of each pixel in the new image is determined by green channel values, since we are using green here. Now we can see that here is the original image, the butterfly image. This is the image which is converted from the color image to grayscale, and this image is the one which we have altered the transparency level by using green as the fourth channel. Now we will learn something about blur, dilation, and erosion. Gaussian blur is the common image processing operation used to reduce the noise and detail in an image. It's named after the Gaussian function, which is a bell-shaped curve used as a kernel or filter in the blur operation. Gaussian blur is particularly effective at smoothing an image while preserving the edges and important features. Now, as usual, we are reading and displaying the image. Here we are using the Gaussian blur function. It's an inbuilt function for blurring an image. Here we are using the CV2.Gaussian blur. The Gaussian blur function applies the Gaussian blur to the input image. The 5,55, that argument specifies the kernel size. A larger kernel in the y direction causes more vertical blurring compared to the x direction, which can create a vertical smearing effect. The zero in the function call represents the standard deviation of the Gaussian kernel, which is set to zero, indicating that the OpenCV should automatically calculate it. Kernel equal to np dot ones 5 comma 5. This code creates a 5 comma 5 5 by 5 binary kernel filled with ones using numpy. The kernel are often used in the morphological operations like dilation and erosion. Use CV2.dilate is used to apply a dilation operation to the input image using the specified kernel. The iterations parameter is set to 1, which means that the dilation operation is applied only once. Dilation is a morphological operation that expands the white regions in a binary image. It can also be used for tasks like enlarging objects and joining the nearby regions. CV2.erode applies an erosion operation to the input image using the specified kernel. The iteration parameter is set to 1, which again means that the erosion operation is applied only once. Erosion is another morphological operation that shrinks the white regions in a binary image. It is often used for tasks like reducing noise, separating overlapping objects, and making the objects thinner. In summary, Gaussian blur smooths the image to reduce the noise and details. Dilution expands region in a binary image. Erosion contracts regions in a binary image, especially the white regions. Now we can see this is the original image we have read, and this is the dilated one. This is the blurred one, and this is the eroded one. Now we will see something related to scaling and rotation. So we are using the cv2.resize function to scale the image to whatever size you want. Here I have given parameters as fx equal to zero point 0.5, fy equal to zero point 0.5, which means that the image is scaled to half of its size. If you specify the stretch to a particular image, we can specify in the form of pixel. Here I have stretched the image by 600 by 6, comma 600. So what is interpolation? In image processing, interpolation is used to estimate the pixel values at non-integer coordinates within an image based on the values of the nearby pixels. Nearest neighbor in interpolation is the simplest method. When enlarging an image, new pixel takes the value of the nearest pixels in the original image. So we will see the difference between image underscore stretch and image underscore stretch using interpolation. So this is the original image using the resize fx equal to 0.51. I have resized into half of its size, and this is using the stretch uh, user defined values 600 comma 600. Now this is the output image of stretch using nearest interpolation method. So we can see a slight difference between the previous one without using interpolation and this, because this uses a set of image pixels to to estimate the value in the non-integer coordinates. Now we will see something related to rotation. So if we use the inbuilt function get rotation matrix 2D, and we are giving here parameters as minus 30. The code rotates the images by minus 30 degrees counterclockwise around the origin 0, 0. The get rotation matrix 2D generates a transformation matrix for rotation. The warp affine function applies the rotation to the image. So this is the original image, and we have rotated the image by 30 degrees. Now we will see an important function in uh, computer vision, which is called the segmentation. Segmentation has many ways, but the typical output is a binary image. Binary image is an image that has either 0 or 1 value. Essentially, 1 indicates the piece of image we want to use, and 0 is every other thing. To get the binary image from the original image, we use some thresholding algorithms. It's a type of segmentation which looks at the value of the source image and compares it with the central value to decide whether that pixel should have the value of 0 or 1. So, for example, uh, let this be the image values, pixel values of some sample image. And here we are setting the threshold as 128. So the values more than 128, we are considering only the values more than 128, for example. So after thresholding, all the values lesser than 128 becomes 0 and the values greater than 128 becomes 1. Similarly, if we set the threshold as 64, all the values lesser than 64 becomes 0 and the rest of them becomes 1. Now we will see two simple ways for thresholding. So the first way is the manual way and it's a slower way. We are using a for loop here for row in range 0 to height and for column in range 0 to width. If the row comma column is greater than the thresh value, which we have set as 85 here, then we are setting that particular value as a white color. The values which has lesser than thresh will remain black. And we also have the second method is the faster one, which is an inbuilt function cv2.threshold. It applies the thresholding directly to the input grayscale image, which is BW here. The function returns the threshold value called ret here, and the thresholded image thresh using the chosen thresholding method as thresh underscore binary, which converts the values above 85 to the maximum value 255, which is white. So this is the original image. This is the original image. This is the image output obtained from the for loop method, which is a slower method. And this is the inbuilt function method. You can see that values of uh, of the image pixels greater than 35, 85 it has become white here, but the darker images which has values lesser than 85, it is not present here, which is black here, because we have set the value as 85, thresh value as 85, and we want to concentrate only on the uh, parts which has more than 85 as a pixel value. So the the ones lesser than 85 is disappeared from here. Now we'll see another method called adaptive thresholding. The image IMG is an input grayscale image. Since we have used 0 as a parameter here, that means the input image is a grayscale. If we use 1, then it's a color image. So we are performing the normal inbuilt CV2 dot threshold method. In CV2 dot adaptive threshold method, the method is used to calculate the threshold value, in this case using the mean value, the average value of the neighborhood area. So here we have set the value 115 as the neighborhood area. The 1 indicates the constant subtracted from the mean or weighted mean. So this is an image, the original image. This is the one using the thresh function. This is using the adaptive threshold function. We can see that this is a better inbuilt method comparing to the normal simple thresholding function. Now we will see one more application related to thresholding. So the first we are reading an image called faces.jpg as a color image. Next, using the CVT color function, we are converting the color image to HSV color space. So now I am splitting the HSV channels into hue, saturation, and value, and assigning it as H, S, and V respectively. Now, using the np.concatenate function, I am concatenating and display the split HSV channels. Now, I am using two threshold functions. The first one here, it applies a threshold to the saturation channel S. Pixels with greater than 40 are set to 255 and the others are set to 0. And here I am applying the threshold on hue channel. The pixel values with greater than 15 are set to 255 while others are set to black. So now I am using a bitwise AND operation between the min sat and max hue. So this operation results in an image where the pixel satisfies both conditions. That is, the saturation value should be greater than 40 and the hue value should be greater than 50, lesser than 50. So this final image is filtered and it is displayed in a window titled Finer. So now this is the original image and this is the split HSV. So this shows the hue, this saturation and value. Now this is the first threshold we applied on saturation. The obtained output is this, and this is the threshold applied on hue filter. Now after using the bitwise AND operation between the saturation and the hue, we are obtaining a final output like this. Next, we will learn something about contours. So once we have done segmentation of an image, the next step is to identify the individual objects. The goal of the contours is to take a binary image and create a tightly fitting a closed parameter around all individual objects in the scene. Each parameter is called a contour. In mathematical point of view, it is an iterative energy reducing algorithm. But conceptually, we can think it as an elastic film that starts at the edges of an image and squeezes in around all the objects and shapes. It creates a boundary around all these objects. One thing we need to be aware is of the idea of neighborhoods and connectedness. Contours will consider any pixel value above 0 as a part of the foreground and any other pixel touching or connected to the pixel will be made to be part of the same object. As the algorithm runs, it tries to reduce the energy or the bounding box around all these objects until it comes to a converged result. So the first we are reading an image called detect underscore blob.png as a color image. And using the CVT color function, we are converting the image into grayscale format. Now we are applying the adaptive threshold image to the grayscale image and it calculates the different threshold for different regions of the image. The fine contour, now we are using a inbuilt function called fine contours. The fine contours is used to detect the contour in a thresholded image. The thresh here is the input image. cv2.retr underscore tree specifies the retrieval mode of the contours and cv2.chain underscore approx underscore simple is the contour approximation methods. There are different methods available in this library. We are using these methods. So using copy function, we are creating a copy of the original image and we are setting index equal to -1, thickness equal to 4 and color equal to 255, 0, 255. These values are for the contour lines, which we will see in the next slides. Now using the draw contest method, we obtain the output like this. So this is the original image. We have converted that to grayscale like this. Now after using the draw contours, first we are finding the contours and we are drawing the contours. So this is the color we specified and the thickness. So these are the contours or perimeters we are obtaining. So if we want to color the portions inside a contour, we can use this method. So first we are the same thing like finding the contours. We are creating a copy of an original image. A blank image is created for visualization. The code iterates through the detected contours, drawing them on the blank image. For each contour, it calculates its area, perimeter, and centroid using OpenCV functions. A red circle representing the centroid is drawn on the image. So here we can see for C in contours, we are drawing the contours and using contour area function, we are finding the area and arc length function, we are finding the perimeter. And using the moments function, we can calculate the centroid value using some mathematical manipulations. And using the circle method, we are printing the circles, that is the centroid as a red color. Since here red means 0, 0, 255, which indicates red. Also, we are printing the area and perimeter. Now we can see that this is the binary image which we have converted from color to binary, and we have created a new blank image, and we have drawn the contours in this image and centroids after calculating using moments function, and red color we are obtaining the centers of each point. Also we are getting the area and perimeter values of each contour. Now we will see something related to canny edge detection. The first step is to read the image as a color image. Next, we are converting to BGR to HSV color space. Then we are doing a simple threshold function to the HSV image. And we are using a function called canny, where we are inputting the color image. Next, next we are creating a kernel with equal to np dot ones, which is a blank image. And using erode function, we are eroding the parts where the values are like 255 minus edges. And using the bitwise AND function, we are merging the erode image and fresh image. And using a for loop, we are calculating area of the each contour after finding the contours. If area is lesser than 300, we are not considering it as it is too small. So if area is greater than 300, we are printing. Then we are drawing the contours. Then using moments function, we are finding the centroid and circle to print the centroid on the image. Finally, we are displaying the image. So this is the input image. After converting it to HSV color space and using normal threshold, we apply this. We obtain this. And using the canny function, we are obtaining this output. And after using bitwise AND operator, we are getting this out. So we can find that we are getting the image of our interest, which is the red tomatoes here. Since we have set the values in the previous uh, methods thresh function as the values nearing red color. So we are getting those as white and others are getting avoided. So this is the final draw. We are also obtaining the contours here and centroid values. Now we will see template matching. When it comes to feature detection, the simplest method is template matching. It searches for a similar pattern between two images. This is accomplished by taking a reference image called a template and sliding it around the other comparison image, taking a difference at every position. The result is a black and white grayscale image with varying intensities showing how well it is matched in each position. So here we are reading a template image as a grayscale image and frame, which is a sample image as layers.jpg as a grayscale image. We are displaying the both images using InShow function. Now we are using a new function called match template, which takes the frame template as parameters, and there are different methods to find the template matching. Here we are using tm underscore ccoef underscore norm. This function slides through the whole. This function takes the template and slides through the whole image and compares the values and stores it in the form of result variable. So we are finding here we are used for this method. We need to find the max location to find the maximum matching area. We are printing the maximum matching area in the form of circle using white color. So you can see that this is a sample template image of football, and this is some children playing football. So this image slides through the whole image and it compares the values of the template image and this image. And the place where the maximum difference is found, in case of tm underscore ccof method, it draws a white area. You can see that where almost the template is matching here and we can find a white line circle here. Now we will see some challenges in computer vision. Variability in visual data. Image and videos can vary significantly due to changes in lighting, viewpoint, scale, occlusions, deformation, and more. Accommodating this variability is a major challenge. Data quality and quantity. Obtaining large and diverse data sets that adequately represent the real world scenario is crucial. However, labeling data accurately and having enough data for robust training remains a challenge. Feature abstraction. Developing techniques to extract relevant and meaningful pictures from raw visual data is crucial for accurate analysis. Traditional methods often struggle with complex abstractions. Robustness to noise and interference. Computer vision models need to be robust against various kinds of noise, distortions, or interference present in the real world data, including sensor noise, occlusions, and varying environmental conditions. And finally, high computing costs. Future potentials in computer vision, agricultural and food industry. It can help in crop monitoring, disease detection, and yield estimation in agriculture. It also plays an important role in sorting and food quality inspection. Industrial automation and robotics. Computer vision plays an important role in various tasks like manufacturing, quality control, and logistics. Environmental monitoring. Visual data analysis can be crucial for environmental monitoring and conservation efforts, such as monitoring wildlife, analyzing satellite imagery for climate studies, and more. Natural language processing integration. Combining computer vision with NLP allows for more comprehensive understanding of multimedia content, enabling systems to comprehend both textual and visual information. Smart cities and infrastructure. Computer vision and technology can contribute to smart city initiatives by enabling traffic management, waste management, infrastructure monitoring, and public safety enhancements.